Well, that's how I got out in 6 years. Okay. Hey, you learned the system. There was no requirement. All you had to do was pass the general exam, and I barely passed it. But barely is good enough. No, yeah. Well, I remember when I came back to interview for the faculty, Professor Elliott, who was a very stiff guy, he looks at me, I'm interviewing for this faculty position, he says, what if I told you you didn't work very hard as a student? Which was ridiculous. I've been working 80 to 100-hour weeks since I was 19 years old. But, I was working 40 hours a week in the lab getting paid as a student. And that was one of the reasons that helped things. I was learning on the job, if you will, and that helped me in the class. And my comments, well, I got straight A's, what difference does it make? So that was not the answer that he wanted to hear. Okay? He didn't care for good enough. Actually, I didn't get straight A's. I got a B in psychology, I got a B in European history, and I got a B in something else. Anyway. Okay, welding of titanium. Anybody have any questions about other stuff? We were gonna, well, dark, oh, we closed those things. Yeah, okay. Titanium, heavy section welding of titanium. In 1980, when the Alpha submarine was launched, and the Navy all of a sudden was shocked because the Soviets had a lightweight, deep diveable, high-speed, non-magnetic submarine, everybody was scared to death. They thought, uh-oh, they just leapfrogged us in technology. Of course, 3 years later, when it was full of cracks and they had to, and also they found out within the first 6 months it was so noisy that you didn't care about the fact it was non-magnetic. You could hear it from miles away. It was a very noisy ship. But first, when it first happened, everybody thought, it's not going to be detectable. It could run faster underwater than our destroyers could on top of the water. It could dive deeper than the collapse depth of the depth charges. Although, as one person from Colorado told me, it doesn't really matter. You get the right type of depth charge. You only have to be within a few miles anyway. My comment was, well, if you start using those depth charges, it's all over anyway. But anyway, my first contract at MIT in 1977 was to do submerged arc welding of titanium. Submerged arc welding I mentioned before. You basically have two heavy plates and it's in a flat position. You pour this granular flux on the top surface of the plate and you run the electrode down through and you can have 600, 800, 1,000 amps. So it's very, very large weld beads, high productivity. That was the process I said Franklin Roosevelt, we think Franklin Roosevelt was talking about when he talked about the new high productivity process. It was invented in 1936 by Union Carbide for steels. And it turns out, because of a completely different economic system in the Soviet Union, the Soviet Union spent, if it was done here, it would be several hundreds of millions of dollars just developing welding technology for titanium. They have a lot of titanium ore. Militarily, it was important, and they had an economic system that didn't really care about things. That basically, if the military said they wanted to do it, the rest of the society kind of geared up for it. And there was a scientist at the Patton Institute in Kiev. The Patton Institute is still today the world's largest welding institute. Boris Patton's father, Boris, in World War II, made a name for himself by welding the armor on Russian tanks and getting them back to the front to fight the Germans. So he was a hero of the Republic. After World War II, Boris Patton the Elder basically was given lots of money in the Soviet system and started the Patton Welding Institute. And it's broader than that. It's kind of a steel institute and all kinds of other things now. It has like 5,000 people, researchers. This is not a small place. His son took over. His son was not only a member of the Ukrainian Supreme Soviet and head of the Ukrainian Soviet, Ukrainian Academy of Sciences. he was a member, one of the 7 at-large members of the Soviet Academy of Sciences. And the Academy of Sciences in the Soviet Union gave out all the research money. So he was one of 7 guys on the kind of governing board for the entire Soviet Union. The Ukraine was the wealthiest at that time of the Soviet republics. And so when the money came to the Ukraine, he was chairman of divvying up the money, the research money, scientific money in the Ukraine. And obviously his institute grew and grew and grew, right? And there was this guy named Gurevich, who I met in 1980. He's passed away since. Gurevich is a wonderful man, honest as the day is long. And I had an opportunity to talk to him. Now, this is 1980, right after they had built the Alpha Sub. And for 3 years, I had been doing submerged arc welding on titanium. This is one of these. This should go to the Smithsonian. This is a submerged arc weld on 1-inch thick titanium 6 aluminum 4 vanadium using reagent grade calcium fluoride crystals. You can't use oxides on titanium. Titanium is so reactive with any oxides. The only thing you can use is chlorides and fluorides. Chlorides are terrible because they pick up all kinds of moisture. Fluorides don't pick up quite as much moisture. They can give off hydrogen fluoride gas while you're welding, little detail. But we used to take single crystals of optical grade calcium fluoride at $100 a pound and crush them up to make the welding flux. And there's the weld bead. It's not a great looking bead. It turns out this, and this is the one I passed around before, and I don't even remember. I just passed this around to show you a titanium flame cut. This is actually 3 submerged arc beads put together. Not a bad weld there, and I don't remember which flux. You'll see some blue flux type stuff still on the top surface of this thing. So those were made here. And this was all for heavy section titanium. And the Navy down at David Taylor had a workshop in probably the summer of 1980. And the first day was Navy Day because for 20 years, the researchers at the U.S. Navy had been trying to weld heavy section titanium. And by heavy section, they meant 1, 2, and 4 inches thick were the kind of things they were welding. And in fact, this was just after the B-1 bomber program got canceled. And the Navy got all the titanium that the Air Force had bought for the B-1 bomber, and they had it stored at the end of the runway somewhere. They didn't have money to buy a welding table in their capital budget, so they made it out of a piece of 4-inch thick titanium. Okay, hey, you don't have money in your budget, you just make it. You make the $1 million welding table, right? Because you can't buy a $3,000 one in your budget. Anyway, they would send me this 1-inch plate, and we would weld it. It turns out the first day was Navy Day, and the second day was Industry Day. I was the only speaker at the Navy Day that wasn't at the Navy, okay? It wasn't a Navy employee. And that was because I had this Office of Naval Research contract. So there's submerged arc welding that you can do. You can do, well, the Navy had spent a lot of time on gas metal arc welding. That was what David Taylor had spent most of their time on. It turns out they built the Sea Cliff. Is the Sea Cliff still in operation? It's the research vessel, deep diving research vessel. There was the Alvin, right? Is Alvin still in operation? Okay, Sea Cliff is a little bit larger. It was built at Mare Island. Originally, in the Sea Cliff was supposed to be gas metal arc welded using the technology developed by David Taylor. When they actually tried to do it, they were having so many problems that they ended up going back to gas tungsten arc welding, which is a very slow process. So you're talking a 7-foot diameter sphere, and I think the Sea Cliff was like 1 1/8 or 1 3/8 thick wall, a sphere. That's not classified. You can read that in the literature. Okay. But this, these things would dive to 20,000 feet or greater. The Alpha goes even deeper than that, but it's even smaller. In any case, so these are deep sea research vehicles. And so the Navy made the Sea Cliff. I think the Alvin originally was a steel hull, but I think they may have switched to titanium. But in any case, the Sea Cliff was the first titanium hull submersible. And it was kind of a demonstration vehicle of how to weld heavy section titanium. The interesting thing about the Navy Day, 1-inch, 2-inch, and 4-inch titanium, industry came in, and there was all these aerospace guys who had welded titanium. The heaviest they talked about was 3/8 of an inch. That was the heaviest experience that American industry had with welding titanium. Most of it was 1/4 of an inch or less. One person talked about 3/8. And it was supposed to be heavy section titanium. So it turns out we proved that this is possible but not economically viable. The reason is the flux is $100 a kilo. So you're talking $50 a pound for the flux. It turns out when you submerged arc weld steel, you use about 6/10 of a pound of flux per pound of steel deposited. In titanium, it goes the other way. You use about 5 pounds of flux per pound of metal deposited. So even if you reuse your flux, and you can't really reuse the titanium flux too much, you're talking, well, even without reuse, you're talking $500 of weld metal deposited for the flux. So submerged arc, we proved, is a viable process, but it's not economical. Gas metal arc is what David Taylor had spent millions of dollars over 20 years developing. The problem is it's inherently an unstable process. And when I talked to Gurevich, who, I mean, I had the KGB agent sitting right here, okay? I told them I wanted to meet with Gurevich. They let me talk to him for 2 hours, okay? And the KGB agent was sitting right next to him. He answered every question, and I knew enough about the subject that I knew he was answering the questions correctly, I mean, honestly, okay? Because the things I knew about, he was answering honestly. Things I didn't know about, he told me, he says, no, we don't use that process, okay? So all of a sudden we learned they didn't use that process on the Alpha submarine, okay? He says, no, doesn't work. You know, he says, unstable, you know? Of course, we've spent millions of dollars and we've been fighting the stability problem. So it turns out one of the processes for heavy section titanium turns out to be gas tungsten arc welding. If you look at the Soviets have 2 books, welding production and welding automatic welding, where they publish their work. In the 60s, Gurevich was publishing papers on what they called, it was translated as semi-submerged arc welding. It wasn't semi-submerged arc welding at all. It was gas tungsten arc, where you use a great big tungsten electrode. This could be 3/8 inch diameter tungsten electrode. You can have 1,000 amps on this thing. And we haven't talked, later this week, we'll talk about plasma jets. But there's a wind that comes off the end of this electrode that's proportional to the current. Actually, proportional to current squared. 800 or 1,000 amps. And you actually significantly depress the surface of the weld pool. So if this is your weld zone, you can just gouge a hole right in the liquid metal. And one of the techniques that was used, the Soviets could weld 2-inch thick titanium with a joint preparation that looked like this. And they do it at 1,000 amps or something on that order, I don't know exactly. They basically would come in here and they could weld a 1/2-inch deep bead in here from both sides by just butting these two things. It was machined, you know, with these little lips on them here. So they'd melt one side here, melt the other side here. Great big weld bead. And then they come in up top with a titanium wire feed into this thing. And in 4 passes, they could weld 2-inch thick titanium. Okay? Pretty amazing. More productive than submerged arc welding, and no flux involved. Actually, there was a small flux. You'd paint on this little coating of some of these specialized chlorides and fluorides. Well, what happened in 1985, when peace started breaking out, and the Soviets were looking for foreign exchange, the Patton Institute started trying to market some of their technology abroad, and they started selling this flux. If you want to get the Soviet flux for titanium for this gas tungsten arc process, it's not submerged arc, and the flux still can be very expensive, except it's made in the Soviet Union, so it's not $100 a kilo. But it's still 10 or 20 bucks a pound, but you're just putting a little whitewash on. Okay, you put hardly any on, and without getting into all the details right now, you can get very deep penetration, very big weld beads, 1,000 amp currents. And so you can weld heavy section titanium. That was one thing. That's one way they used to do it. Another was electro slag. And it turns out Soviets actually published a lot of this stuff in the 60s, and in the early 70s, all of a sudden they quit publishing anything about it. Surprise, surprise, because they were getting close enough to commercialization, they realized they were actually going to use it. But Gurevich was a pure scientist. He was not a politician. He didn't care about any of those things. He was a great man. Anyway, Electro slag, I have a heavy section plate like this. Pardon me? Oh, this was the end of, maybe I'll talk about Electro slag tomorrow. This is an interesting story with the KGB guy. This was the beginning of the Reagan administration. And Carter had started detente, okay, trying to work together. And I was a young assistant professor in 1976 or 77. In about 78, Carter had started this openness. And Professor Grant here, who's now retired in about 80, had actually grown up in the Soviet Union until he was 5, became a professor at MIT. And the National Science Foundation put him in charge of the electrometallurgy program. The National Science Foundation, as part of President Carter's scientific exchange, had chosen electrometallurgy as one of the topics with the Baton Institute. And so you got all these big name full professors around the country who'd never been able to go to the Soviet Union. They all wanted to go. First time they go, 37 of them go. Wow, this is a junket. And Professor Sekeli here. So Professor Grant spoke Russian because his parents came from there. Professor Sekeli here, who actually left Hungary in '56 as a freedom fighter and was educated in Imperial College and had learned Russian in Hungarian schools, went on that trip. Professor Flemings here went. I was a lowly old assistant professor, and they didn't even tell. Professor Grant never even told me about all this stuff, right? They were going to the Baton Institute, even though it's my research area and everything. So he was very helpful to me. Basically ignored me. So the next time they went, the Soviets, when they finally got through customs and everything, the Soviets whisked them off to this big state dinner. And then at the end of it, they asked them to pay for it. The Americans had to pay for the state dinner. And anyway, so the next time they go, only 6 Americans go to the Soviet Union. And the last time, this is after Reagan started, and he basically was closing it down. And the only person who wanted to go was Professor Sekeli, but he was going to have to go by himself. So they decided that I could go with him, and I wanted to go. It's one of the last chances anyone's going to get to see any of this stuff. Plus, the FBI wanted me, or the CIA wanted me to go to talk to Gurevich, which is true. I had to be debriefed. Anyway, the KGB, they used to come visit us here, and we had all identified this guy as the KGB agent because there were like 6 or 7 Soviets or 10 Soviets who came to visit MIT during the Carter administration. And there was this one guy who just passed away recently, Medivar. He was one of the 3 guys underneath Baton at the Baton Institute. He was a Soviet Jew who was actually a member of the Ukrainian parliament. For a Jew, that was a big deal, okay? Very unusual. And then there was Mariinsky. The parliament palace in Kiev is called Mariinsky Palace. So Mariinsky's kind of a big name. And Mariinsky was a KGB agent. And you could tell because you'd be over at the faculty club, socializing with these people, and you'd ask a technical question, and one of the underlings would look at Mariinsky to see if it's okay to answer. Everybody would except Medivar. Medivar just answered. He didn't care about Mariinsky, okay? So turns out we were at the very end, and they were doing everything they could to keep the channels of communication open with Sekeli and myself. So they let me talk to Gurevich for the whole hour, okay? And they didn't really, I don't know if they probably knew all kinds of things, but nonetheless, that's the answer to your question. Reagan was shutting everything down. The Soviets were doing everything to try to keep it open. And the interest in the United States was declining too, and so because of the way they treated us when we went over there. But it was also funny because Professor Flemings, who was head of the department here, was a big guy in this exchange, and he doesn't remember people's names very well. Professor Bowen's name was Kent, and he used to basically call him Ken Bowen. Okay, this is one of your colleagues, and didn't even know his name, how to pronounce it. So Professor Hadaway and I used to say, well, Professor Merton Fleming's, he goes by Mert. We said, well, the T's silent, so we called him Mur. Okay, but anyway, Professor Fleming's couldn't remember names very well, so he would call this KGB agent, whose name was Marinsky, he would call them Marinchek, because that's sort of a Soviet name, right? So he called him Marinchek. And Marinsky would just seethe. You could see this guy, you know, because Flemings couldn't remember his name and always called him Marinchek. What got really funny was when Metavar started calling Marinsky Marinchek. And all the rest of us knew what was going on except Flemings, except Professor Flemings. And I mean, basically, so there was a lot of fun with these people. Okay, I can tell you all kinds of stories about it. So anyway, electroslag. I'll start talking tomorrow about electroslag of titanium. The two primary ways they built the submarine was this semi-submerged arc, gas tungsten arc, which is it's a submerged arc in terms of lays down big, very productive beads, and electroslag, which is this vertical welding process. And I passed around the electroslag weld. The first electroslag weld made in the United States, to our knowledge, in titanium, was made downstairs in the weld lab in 1980, because I was at that workshop, and at the second day of the workshop, I started, and we were talking about how could they build this submarine, you know, how did they do it, and all of a sudden it hit me. I'd seen some papers in the 60s from Gurevich about electroslag welding, that you could electroslag titanium, and then I knew I was already running into the cost problem of the flux, and I realized that electroslag, 1 pound of flux could lay down 50 pounds of weld metal. So you could afford to use the flux if you used a different process. So we went back, and a few weeks later we made an electroslag weld. Not this one. This was made at Oregon Graduate Center because within a year the Navy classified all this. It's all unclassified now, but you know, it was classified fairly quick. But when titanium ships were a big deal, all of a sudden, I basically, at that point, MIT doesn't do classified research on campus, so I basically got out of it at that point. But anyway, we'll talk some more about heavy section titanium welding next time. Okay, we were talking about submerged arc and gas metal arc and gas tungsten arc welding of titanium. And I was starting to talk about electroslag welding of titanium. We actually do a lot of electroslag welding of steel. Electroslag is a process for vertically welding heavy plates. I'm trying to do a three-dimensional perspective here. If I have two plates and I have a gap, and that gap could be an inch, inch and a half wide. The plates typically, we do sometimes electroslag weld 1-inch plates, but we prefer to do 2 or 3 or 4-inch plates. You basically put a copper dam on the back side and then another one on the front side. You put a steel or a titanium plate, in this case, on the bottom to create a base. You pour a little bit of this submerged arc type flux, this granular sand in here. You feed a wire down in here, and I now have a casting cavity with titanium plates on 2 sides and water-cooled copper on the other 2 sides. I strike an arc down here on this consumable base plate that I'm going to cut off later. That arc melts everything just like in the submerged arc process, although in this case I put a high enough head of flux that glassy molten flux layer collapses the arc. It's too heavy for the arc. And now I have a layer of molten slag. In this case, it tends to be for titanium, calcium fluoride, and strontium fluoride mixtures, because those are the highest melting fluorides. And I feed the wire in here while I'm continuing to pass 1,000 amps, 2,000 amps. If I'm doing a 1-inch plate or a 2-inch plate, I may have 1 wire feeding in here. If I'm doing a 3 or 4 or 5-inch plate, or people have done 10-inch plates, you have multiple wires going across. You still only keep the gap about inch, inch and a half, but you basically make it a long, narrow weld. And the wire feeds in, and it resistively heats. There's no arc except to start the process. the arc starts by melting everything. Once you get this layer of molten fluoride, which might be at the end an inch, inch and a half deep, you just feed the wire in there while you're passing 1,000 amps, and it resistively heats the molten fluoride, electrical resistance heating. And the wire is feeding into this 1,400, 1,500 degree centigrade molten flux. With current going through the wire, you melt off drops of wire, which just make a casting going up. Turns out in steel, in steel you don't use, you might use a high calcium fluoride, but you actually use calcium oxide, aluminum oxide. You make with containing some fluorides to make this flux. You actually should have seen in one of the videos Electro Slag overlay, which is maglay. It's a maglay process. Maglay, where they use, instead of wires, they use sheets of things like a nickel-based alloy, and you want to put it on a carbon steel. You basically can lay it horizontally across the thing and coat, make a composite structure with steel with maybe a half-inch layer of high temperature or high cost material on top. In any case, Electro Slag is a vertical welding process. You can go at probably anywhere from 5 to 10 feet per hour. In a heavy plate, that's really productive welding. I mean, very, very productive. You know, I've passed this around a number of times, but this is a cross section of an Electro Slag titanium weld that was made at Oregon Graduate Center on a classified contract in the mid-'80s. And the weld zone ends up, you're melting back some of the base plate. You can actually see the mold on here of the copper chill blocks on either side, and you're basically making a casting going straight up. Turns out titanium melts very, very fast. In fact, the first welds we made, which were the first ones made in this country, where we basically, turns out the titanium melted off so fast we really didn't get fusion to the base plate. Turns out we later learned you can't use DC current, you have to use AC current to get this type of weld. But that's neither here nor there. But very, very efficient process, probably used in the alpha submarines, that's all I say. Okay.
How wide is the gap? Is there a limit on how far apart the plates need to be? Like how far apart?
Well, this one's a little over, this is like 1.25 inches. You don't want to make it too wide because then you just have to feed more wire in. If you make it much less than 3/4 of an inch, you start having problems feeding things down in there. You don't have enough room to feed this long wire in there. You make it much bigger than that and you're losing productivity because you're putting in more weld melt. So now, I assume you're talking about the width this way. The width this way, I mean, people have talked about is welding 4 great big forgings together. So they talked about 3-foot, people have tried like 1 foot or 2 foot wide Electro Slag things. It turns out there's a process called Electro Slag remelting, and it turns out, let me back up, I talked about the Patan Institute. Professor Patan, the son of Dr. Patan, this was his process that he really invented right after World War II. Right. There's arguments over whether he invented it or whether some people here in the United States actually invented it, but he ended up perfecting it big time. And he was the guy who was on the Supreme Soviet Academy of Sciences and parched up the money all around the Soviet Union, and then was head of the Ukrainian, which meant he was in charge of partitioning it in the Ukraine. And one of the reasons the Patan Institute is a 5,000 person research institute is not because it just does welding. They actually started doing what's also called Electro Slag remelting, where you can have an ingot that's 24 inches in diameter, and you remelt it. I mean, it's already a molten, it's in a great big steel casting. You remelt it through this flux, and the flux purifies the steel. And Professor Sekeli, who's passed away now, but he was the one that I went to the Soviet Union with in the 1980s. In 1980, I remember we were there in Kiev, and they were bragging because of the 150 million tons of steel that they made in the Soviet Union. Something like 80 or 90 million tons of it was Electro Slag remelted. Well, in this country, maybe 1 million tons out of 100 million tons or 150 million tons was Electro Slag remelted. Because In this country, you only went to electroslag remelting when you needed exceptional quality. Okay? Like you needed a tool steel with very small inclusions and uniformity. You're basically taking a big ingot and giving it a small casting volume, because the solidifying layer of metal here is basically just a little weld pool, if you will. It may be half an inch deep. It's not a great big 2-foot wide casting. It cools very slowly, so you can get very homogeneous, very fine-grained, a relatively fine-grained structure. But it's an expensive process. You're completely remelting what you already melted, and so it's like making the steel twice. And so we only used it for very expensive, very high-quality steel in the United States in the 1980s. But the Soviet Union, over half of their steel was electroslag remelted. They were bragging about it. Professor Spelly says that's because, he says to me at dinner, he says that's because the quality of what they make the first time is so bad. They had to electroslag remelt it to upgrade it. Okay, but that's one of the reasons that the Baton Institute is so big, is that it basically was a steel making facility, not facility, but research center. In addition, they train about 5,000 welding engineers a year at the Baton Institute. From all over, they used to come from all over the Soviet Union, which made quite a difference. In this country, we educate about and graduate about 50 welding engineers a year, whereas in the Soviet Union, it's about 5,000. And I remember in the 80s, in the Alpha sub era and stuff, the Navy was very interested. Do we have a welding engineer gap? Should we be educating more welding engineers? And that's a philosophical question. Okay. So far as building heavy structures, so I talked about the Seacliff submarine. I found here in my notes, 7-foot diameter sphere. It was on the order of 1.6 and 1.8 inch thick wall. Originally, they wanted to use consumable gas metal arc, where you lay down maybe 20 pounds an hour. They ended up using gas tungsten arc at about 2 pounds an hour. Obviously, way over budget. Built it at Mare Island Naval Shipyard because there was no one who could do it industrially, had that kind of experience. And the Navy wanted to get experience with it. Now, the problem with titanium is even a fingerprint on the titanium can cause porosity in the weld. Titanium is one of the most reactive metals we have. It will react with oxygen, nitrogen, carbon, sulfur, reacts with everything. And in fact, it is virtually impossible to cast titanium except by what we call skull melting, where you use a water-cooled copper crucible. You put the titanium in there and you arc melt it or electron beam melt it from the top, and you use the temperature gradient, so you're melting the titanium in a solid shell of titanium. You basically have a temperature gradient from the water-cooled copper shell, and you have this skull of solid titanium, and the titanium you're melting is being held inside a titanium crucible, if you will. It turns out that people are trying to develop some sulfide materials as crucible materials for titanium, based on some work that John Shipman, who was head of the department here in the 40s and 50s, up to 1962, he had done some work on uranium, trying to melt uranium back in the Manhattan Project down in the basement here, and trying to develop some crucible materials. So people are today still trying to do that for titanium alloys and stuff. But basically, to weld titanium, it's a white glove procedure. And I've tried to explain this to various people. When people said, well, we're going to build a titanium submarine, they don't talk about it anymore, because no one wants to go to Congress and say, we're going to build a submarine in 10 years that will put us right where the Soviets were in 1980, right? It's not a strong selling point. So now they talk about building composite submarines, or going to stainless steel submarines, or whatever. In any case, I used to explain to people, you are not going to build a titanium submarine in any of the existing shipyards. You'd have to basically, flatten the whole thing and start again, because people welding titanium should be wearing white gloves to keep fingerprints off the titanium. The shielding for the argon, you have complex shields. If you get the least little bit of air in there, you contaminate the titanium. the fracture toughness goes to pot, and you have some serious problems. So they have built things like the Sea Cliff, but you have very elaborate manifolds where the argon comes in. You typically have to have trailing shields that can be 6 inches behind the arc. Now you start talking about complex shapes, and you're going to have special shaped shields whenever you're welding these things. There's a book I've got downstairs. It's in Russian, so it's all Cyrillic language. It doesn't help you much. But it has a picture of, this is Gurovich's book, and I actually have a translation that, of about 80% of it that someone did for the military. But they have pictures of people in spacesuits inside a room this size, and they put the people in a spacesuit, and the room is filled with argon, so that way they can't contaminate the structure. Okay? It's a completely different philosophy of how you build these things. You can do the gas tungsten arc of 2 inch thick. I showed you yesterday how you can do 4 passes, 2 inch thick material. I showed you how you can do vertical welds and electro slag. In fact, someone asked me yesterday why at Electric Boat they, or actually I don't know if they asked me why, but I told them at Electric Boat, when you're making the cylinders for the 30-foot diameter cylinder for the hull, they actually put in about 4 vertical welds. So they do vertical up welding, which is like electro slag. They don't do electro slag because the problem with electro slag, with the speed of this process, you get heat affected zones in this. They can be an inch thick, okay? Because this is, electro slag has a heat intensity equivalent about like an oxyacetylene flame. And so you end up with very, very big heat affected zones, very, very large grain size. Remember, small grain size is good in steel. Gives you good impact toughness. Electro slag welds have huge grains. I mean, you can see them with your eyes, some of them the size of a dime. Terrible impact properties. So we just build bridges out of them. Electro slag welds primarily. Or skyscraper foundations or something like that. Things where we don't think we need impact toughness until we go to California. Anyway, at Electric Boat, to weld the HY80 or HY100 hull at Quonset Point, they actually roll the plates, and they have the stiffeners on here already, some of them, and they stand them up vertically, and they weld upward. Now, a vertical weld is slower than a horizontal weld, but there's 2 reasons why they do this. One is I can make these 4 welds simultaneously. And so 4 welds at once is faster than 4 welds one at a time by a more productive process. So you can weld faster when you're doing 4 stations rather than 1. The other thing is you have more distortion control. This thing has tolerances going across here in the millimeter regime on 30 feet. This thing has to be circular within tolerances that I don't know about, but I know it's in the millimeters, a few millimeters, okay? And the reason for that is because it's an external pressure vessel, and any type of out of round leads to buckling. So, so that's one of the ways you do that.
Tom, do you know how they weld the bicycles at Merlin?
No, I haven't been to Merlin to see the titanium bikes, as far as I know. Although I thought it was just straight gas tungsten arc.
It is.
Okay.
I think they fill the tube with argon and then use a great big cup on the outside.
Oh, okay, yeah. I mean, okay, so that's, if you've been there, Merlin's a place around here that makes titanium bikes, $3,000 bicycles. And I did have some students when I was department head some undergraduate students did a little project up there, but I never got up there. I was department head at the time. But it takes a little skill to weld titanium. The other thing, another prototype, the DARPA built 2, this is about this would have been about 7 or 8 years ago, 2 4-foot diameter, 50-foot long submarines. Building them was not classified, but what their mission was going to be was classified. I have no idea what the mission was. I wasn't involved in that. But the Draper Lab over here was responsible for designing and building these things, and they had to build them all. The first one had to be built in 6 months. This was a rapid prototyping thing after the Gulf War. They wanted to show that within just a few months you could build some complex military system. And so they came over, Draper came over to me and said, well, can you help us on this? And it turns out it was like 1/4 inch thick plate we had to weld, and we had to put the stiffeners on, of course. Most of that, since it was only 4 feet in diameter, we went down to Connecticut to the aerospace folks, and they're building 4-foot diameter titanium circles all the time. And so we did electron beam welding, we did some diffusion bonding, you know, depending on and we probably did some gas tungsten arc to finally put them together. Most of it was electron beam welding, because the aerospace industry has the facilities for that. But you couldn't build a big submarine unless you came up with brand new facilities. No one's got those types of facilities. Anybody got any other questions on welding titanium?
In that electro slag process, what keeps the molten metal from bonding with those side plates?
That's water-cooled copper. It freezes up against the edge.
Okay.
And if
And
you-
break them off or something?
Yeah, you knock them off with a hammer, but I mean, the water-cooled copper has such good thermal conductivity, as soon as the metal sloshes up against it, it freezes. And then as it cools down, it pulls away. Okay, so it doesn't really weld to it. And it turns out titanium can tolerate a little bit of copper.
Wouldn't that significantly affect the weld properties on those edges then? Or-
No, titanium, some titanium alloys have a little bit of copper in them. Okay, but you really don't get much copper in there. I mean, I can actually still see on here. You can see a little copper color where it actually did, but just a very small amount. Okay, where it kind of bonded to it. Hit it with a hammer, it knocks right off. Okay,
And that slag puddle that just kind of floats on top of the molten metal?
just keeps floating on top, and so you end up using a couple of pounds to make a 10-foot long weld.
No big any kind of impurities from that mixed into the...
You do, actually. This has to have an argon shield on top to keep the air out, because otherwise you could entrain air underneath the slag and into it. Steel, you don't need an argon shield.
I mean, you don't have any problems getting calcium or fluoride into your weld metal?
No, they don't react with the titanium. Okay, they're the only, some of the only things that don't. One of the problems, though, is the calcium fluoride. The reason it needs to be reagent grade, the calcium fluoride will pick up moisture from the air, and if you heat it up while it's moist, the calcium fluoride reacts with the moisture to form calcium hydroxide, which is going to get oxygen and hydrogen into the titanium, which is bad. Calcium oxide and hydrofluoric gas, hydrogen fluoride gas. So that's not so great. I mean, you have to now, have some ventilation procedure if you do have any moisture, but you want to keep the moisture down, which is why we had to use reagent grade fluxes. If you have a 0.5% calcium oxide impurity in your calcium fluoride, weld's garbage. Okay, you have to be down. In fact, the little sheets I had, we were down in the 100 parts per million calcium oxide. The only way you get that is you actually have to have a platinum to make the calcium fluoride flux. You have to have a platinum furnace and use hydrogen fluoride gas to get the oxygen impurity out of the calcium fluoride. And that's what you have to do if you want to make an optical quality crystal. And that's why these things are so expensive. If you look in Gurovich's book, he's got a whole chapter on how the Soviets used to mix ammonium fluoride with the calcium fluoride to purify it and get the oxygen out. But there, they just, they didn't care if they killed some of the workers or people went home with, hydrofluoric acid in their lungs. They're not going to die for a few years, so it takes time for the bones to decompose.
You're saying the vertical welds take longer on those sections. Why does that take longer to get vertical weld done?
Well, these are not electroslag vertical welds. These are an arc weld. You have to weave side to side. You can't use as much current if you have a big weld pool. Remember, the surface tension will only hold, surface energy is dominant at about 3 millimeter size. When gravity becomes dominant, I mean, the two of them are equal at 3 millimeter diameter sphere. My weld pool, if I get much bigger than a centimeter or so in the size of my weld pool, it'll just all flow down by gravity. So, in a flat position, I can have very big weld pools that are an inch across because gravity's holding it where I want. I'm welding overhead, I'm welding vertically. I got to keep the metal in there by surface tension, which means the weld pool can't get very big. I end up using, instead of 500 amps, I'm using 150 amps or 200 amps. Okay, just can't use so much power. Gravity. If you want to build them in space, let's build them on Mars. No. The other patents, let's see, 3 of them are on diamond brazed grinding wheels. In fact, I was going to bring one of those up. I forgot about that. And those are the ones that kind of cut the concrete on the road. So we ended up with a better brazed alloy that gives 3 times the life and stuff. Anyway, okay, ready? What?
Is that the same sort of cutting machines to drill rock, take rock samples, core samples?
Yeah, basically. Yeah. Yeah, I should bring one up. If I remember tomorrow, I'll bring one up. It's just, they're called single point diamond tools. Well, they're actually not single point. They're multi-point. What do they call them? Anyway, they have about millimeter sized diamonds. So these things are pretty nasty. I mean, if you rub, if you were to abrade your skin, it would really cut through it. But they're brazed onto a metal surface. And you just got these little diamonds sticking up about 0.5 millimeter above the braze. And it turns out their failure mechanism, the student showed in his thesis, was basically fatigue of the braze because of the residual stresses, because of the difference in coefficient of expansion between the diamond and the braze. He developed a new type of braze alloy that was a reactive braze alloy that had about half the thermal coefficient of expansion as the regular copper alloys, and therefore it gave 3 times the fatigue life. Okay, I mean, if you went, we go out to Norton and we would just cut concrete, and you could cut for, typically they run those things out in about an hour worth of use. Now they do most of this grinding at night, right, and stuff, but they on the highways, but basically they have to stop and change the wheels about once every hour. With his delays, they only have to do it once every 3 hours. The paper was rejected by the Welding Journal, even though we had measured the coefficient of expansion of the braze alloy in a machine. Okay. It turns out that they rejected the paper because the person says no copper alloys have a thermal expansion coefficient this low. Well, it turns out it wasn't a copper alloy. He had, it was a complex alloy, but he would take copper powders and tin powders and zirconium powders, and actually zirconium hydride powders, and titanium hydride powders, and carbon, black, soot, and there may have been a couple of other things in there. But basically what happens is the zirconium hydride and titanium hydride decompose as you heat them up. And so now you end up with pure zirconium metal and pure titanium metal. And the copper tin was the basic kind of matrix of the braze alloy, but we were really making a composite that had, when you're all done, titanium carbide and zirconium carbide. So it was half ceramic and half copper. Well, these ceramics have low coefficients of thermal expansion, and the copper has a high coefficient of thermal expansion. The guy was right about that. But the whole composite braze alloy had about an intermediate coefficient of expansion, and that met. And we had a finite element model, but the Welding Journal, this reviewer rejected it because he says no copper alloys have that. Even though we provided him the data, he just didn't want to believe it. And at this point in my career, I'm not going to deal with these morons. So we sent it somewhere else. Published it somewhere else.
This is kind of really probably, but what is ceramic?
A ceramic is something that's ionically or covalently bonded, basically. Okay, they're usually hard and brittle, but it's a good question because a lot of your what they call intermetallics, let's say nickel-3 aluminum. Is that a metal or is that a ceramic?
Yeah, because you said a couple times that two metals joined together were ceramic. I thought that a ceramic was something completely different.
Well, it gets. I don't remember saying two metals joined together were a ceramic, but certainly, if I have an intermetallic compound, like I diffuse aluminum and nickel together, I'll form nickel aluminide NiAl or Ni3Al. Okay. Those actually have a very strong covalent nature to their bonding. I mean, they have a specific stoichiometry, okay, 3-to-1 or 1-to-1. Same thing with titanium and aluminum, okay, or niobium and silicon, or whatever. Well, silicon is sort of, I mean, ordinarily you think of a ceramic as one thing from the right side of the periodic table and one thing from the left side of the periodic table. They come together in either ionic or covalent bonding in a very specific stoichiometry ratio. Okay, in a metal, when metals mix together, they mix over a wide range of compositions, where ceramics have a very narrow range of compositions. Well, it turns out the world is a continuum, and you can't say this is a ceramic and this is a metal. There are intermetallics, what people call intermetallics, that I would say that behave like ceramics. They're covalently bonded, they have a very specific stoichiometry, they're brittle because of their covalent bonding. And so it's not clear to me exactly how you differentiate a metal or a ceramic, except for the fact that some people would say metals have metallic bonding with free electrons, whereas ceramics tend to be insulators because of their ionic or covalent nature. However, you get into problems with that because titanium diboride's an electronic conductor, and everybody would say that's a ceramic. Is carbon a ceramic or is it a metal? Well, it conducts electricity, although diamond is definitely considered a ceramic because it's covalently bonded and it doesn't conduct electricity. I don't know that there is a precise definition of what a ceramic is. It's kind of like, you know, I recognize it if I see it. You know, it's like obscenity. Right? Does that answer your question? It's not an easy answer. It's not an easy question to answer for me.
Actually, probably better for that answer.
Yeah. Okay, so it's, I mean, we all, I mean, most people, well, concrete's a ceramic, okay? But, you know, why do I define it as a ceramic? Well, if you actually get up through history, the metals were reduced from the ores and the ceramics were things that were not reduced from an ore that were kind of put together. But science has made all of those distinctions, just kind of wipe them out because we really have a continuum in properties. Other, a polymer? Well, polymer is a little easier because a polymer has a backbone, a linear backbone, typically of carbon, but it doesn't have to be carbon. It can be a silicone, which is an SiO backbone. Okay, silicones are just a backbone of silicon-oxygen bonds, whereas most of your polymers are going to be a bunch of carbon bonds. Now, you may have some nitrogens in there, okay, or whatever, every now and then on an end or something or on a branch. But the polymers are typically covalently bonded chains, and they can have branches off to the side, and they're van der Waals bonded in between. Okay, but does that, anybody want to take issue with that? I mean, again, we in the materials field, we kind of say, well, we know what a polymer is. I can think of a number of cases where polymers, metals, and ceramics are all kind of fusing together because we have electrically conductive polymers now. So you can't distinguish it in terms of its electrical characteristics or its light characteristics. I mean, we actually engineer things now such that we can actually kind of make one thing that traditionally didn't have a certain property, make it have a property. Like polymers were always great insulators, and now you can make them electrically conductive. And they like to talk about the polymers that are electrically conductive. I remember listening 15 years ago to a professor who's a young professor here who left here to go to a chemistry department, and now is head of the chemistry department down in Virginia. And he says, well, he was working on these electrically conductive polymers, which were based on polyacetylide. Okay, well, this has nothing to do with welding of aluminum, but we can do welding of aluminum tomorrow. Polyethylene, well, ethylene is CH2H4, okay? It's a double bonded carbon and 4 hydrogens. Polyethylene is about your simplest hydrocarbon, and it basically has 3 hydrogens on the ends, but the carbons have 2 hydrogens in between. So, you know, So polyethylene has a formula of C to the N H2N plus 2, because I got the two end hydrogens, and I got two hydrogens for every. Well, what happened to the double bond? Well, the double bond, when I polymerize this, the carbons link together. So it turns out polyacetylene, if acetylene is this, C2H2, polyacetylene is actually this is methyl. I can't remember. Polyacetylene is maybe, I guess, well, how's it go? Maybe it's this, if I remember. I'd have to have another hydrogen there and a hydrogen there. So, in any case, polyacetylene has got some double bonds in here. It's a bunch of hydrogen, it's carbon backbone, but every now and then you get some double bonded carbons. Because you took the triple bond, and when you polymerized it, you got something like that. I'm not sure if that's polyacetylene or not, but it definitely polyacetylene has some double bonded carbons in the chain. And those double bonded carbons actually provide some free electrons. And those free electrons give it conductivity. Anyway, this one person was giving a talk in the Chipman room to a bunch of people from industry. He says, well, we're going to start using these electrically conductive polymers in all kinds of applications because they have a lower specific electrical conductivity than copper. And why would you be interested in specific? Specific electrical conductivity is the conductivity divided by the density. Any specific property is related to the specific weight. So if they're low density, then they have a pretty good electrical conductivity. They can have a lower specific electrical conductivity than copper. Well, copper's got a density of almost 9 compared to 1 for water. And so basically what he's saying is the electrical conductivity of some of these things was less than 9 times lower than copper. And I thought, wow, that's pretty impressive. And then I started thinking, hold on. I didn't think about this until I was shaving the next day. I often get my inspirations at 5 o'clock in the morning when I'm shaving. I thought, wait a second, this doesn't make any sense. If specific electrical conductivity was the material property of choice in a motor generator system, I would be using aluminum today. Because aluminum has a density of 2.7, and it has about 60% of the electrical conductivity of copper. So it's got 1/3 the density and 60% of the electrical. Aluminum has a higher specific electrical conductivity than copper. So if I was interested in designing a motor generator set of something that has a higher specific electrical conductivity because it's rotating, and that was his argument, you have these stresses when it's rotating, so you want high specific electrical conductivity. If that was true, I wouldn't use copper in my motor windings. I'd use aluminum. But they use copper. Why do they use copper? Because electrical conductivity is an important thing. You're generating too much heat. And so you want good electrical conductivity, and you can design around the weight problem. Okay? So you have to be careful. When people are selling you new materials, they can throw in a very simple word like specific electrical conductivity. I mean, if they just said electrical conductivity, they couldn't make their statement. But if they say specific, they can make this grandiose statement. But they're pulling the wool over your eyes unless you can stop back and think about, well, is that really the design parameter of choice? No, it's not. Well, I realized the next day, shaving. Okay, and I use that as an example now how material scientists try to pull the wool over people's eyes all the time. Okay, but it's not just material scientists, it's everybody. People are out selling, they're trying to sell what they know, not what the world needs all the time. Sometimes the two coincide. Okay, another digression. We should get to welding of aluminum alloys. Any questions on, if you ask another question, we'll never get to welding of aluminum alloys. Aluminum alloys come in a number of varieties. There's 1,000 series. Well, actually, I separate it. They come in heat treatable and non-heat treatable versions. So the non-heat treated alloys are generally the 1,000 series, the 3,000 series, the 4,000 series, and the 5,000 series. And this is a designation from the Aluminum Association. The 1000 series are 99% plus aluminum. Good for aluminum foil, good for electrical conductors. We do use them as electrical conductors because they're cheaper than copper. The 3000 series are alloyed with manganese, used for beer cans, Coke cans, a few other applications. The manganese adds a little strength to what is otherwise a mostly aluminum alloy. So these 3000 series alloys, usually 98% aluminum, but you add 1 or 2% manganese to increase the strength. The 4000 series alloys are aluminum silicon based, and by and large, for the wrought aluminum alloys, these are just welding electrodes. Now in casting, aluminum casting, which they go by different type of designation, there are lots of aluminum silicon casting alloys. Most of the engine blocks in cars are aluminum silicon cast alloys, but they're not part of the, these 1000 series, are wrought alloys, the ones that are deformed to give them shape. 5000 series are magnesium alloys, and the aluminum magnesium gives you the solid solution strengthening. Typically, so we're doing solid solution strengthening. Essentially, these elements just go into solution, harden up the crystal lattice against dislocation movement. These will have 4 to 20 KSI strength in the annealed condition. Yield strength, and they'll have 18 to 40 KSI work hardened. Work hardened means I've done cold deformation on them. And so when I weld these things in the heat affected zone, I'm going to anneal it. And so even if I get 40 KSI in the base material by mechanical work in deforming it, I'm going to lose some of that in the heat affected zone. I may not lose it all, but certainly I can certainly design alloys that will give me, even after welding, 20 KSI, maybe even 25 or 30 KSI in some cases, in these non-heat treatable alloys. In the heat treatable alloys, we have the 2000 series, the 6000 series, 7000, and the 8000 series. These are copper-based alloying, magnesium plus silicon, zinc, and this 8000 series is just other, everything else. Heat treating of aluminum alloys, you typically have a phase diagram where this is the percent magnesium or copper or silicon or zinc. And this is 100% aluminum over on this side. You have a eutectic type of diagram where you have liquid. This will be alpha solid. That's aluminum solution. And you'll have a compound over here. It could be copper 2 aluminum. It can be magnesium 3 aluminum or 2 aluminum. I can't remember. Magnesium, well, I can't remember. It's magnesium 3 Al2. I can't remember exactly. But all these form intermetallics. And so if I heat the material up to this region, I'm above the solvus. I can dissolve all the magnesium or all the copper into the solution. I then quench it down to room temperature, and I heat it back up to some intermediate temperature below this solvus line, and I precipitate out little particles of these intermetallics. That's the heat treatment I do on the aluminum alloys. Some of the aluminum alloys, actually this type of aluminum solid solution strengthening was discovered around 1910 or so. It was explained in the 1920s. It was one of the first great explanations of using X-rays in material science to actually see these little particles, which are nano-sized particles. They're like 30 to 100 angstroms in size. About 10 years ago, the National Institute of Standards and Technology was able to take a sample from the Wright brothers engine, which was a cast aluminum copper engine, and actually analyze it, because these things will actually age the particles will grow even at room temperature. And here the Wright brothers engine was one of the oldest pieces of aluminum alloy that would have these little precipitates. The Wright brothers didn't heat treat the engine, they were just throwing copper in there to strengthen the aluminum. Cheap aluminum didn't become available until the 1880s when Charles Martin Hall in the United States and I think it was Pierre Herault in France independently developed the Hall-Héroult process to refine aluminum oxide. Before that, the only way you could get metallic aluminum was to take sodium metal and reduce the aluminum oxide. You didn't have a lot of sodium metal around, and so it turns out aluminum was more valuable than gold before 1880. The top of the Washington Monument has got a little 8-inch spike of aluminum because it was more valuable than gold, and so the top of the Washington Monument has got this little piece of aluminum on it. It turns out King Louis of the 16th or something of France, his dinnerware, okay, was aluminum because it was more valuable than gold. Okay, nowadays it's not so neat. Anyway, anyway, the 10 years ago, the National Institute of Standards and Technology went and did some scientific studies on the growth of these precipitates in the Wright brothers engine because they had been aging for 100 years at room temperature at the Smithsonian. Okay, from that they were able to now extrapolate. They had the short-term data, and now they had one data point at 100 years. And it's not often you get a data point at 100 years. Okay, on how fast these particles grow. I think I mentioned to you that the Concorde, when it starts to fly again, it flies not on speed, but based on skin temperature. It's made of heat-treated aluminum alloys. And if it gets too hot, it's going to lose its strength over time. So some of these alloys don't diffuse very fast at room temperature, but certainly you do the precipitation heat treatments at like 250 degrees Fahrenheit. It doesn't take much temperature to grow these little precipitates. In any case, to finish up for today, the types of strengths, if I can find where I put my notes, types of strengths I can get with these alloys are 7 to 14 KSI annealed, and I can get 25 to 72 KSI typically heat treated. So 72 KSI, that's yield. That's significantly stronger. That's double the strength of a garden variety steel. It's nowhere near the strength of a heat treated steel. I mean, it's less than a third the strength of a heat treated steel, but it's for its density, it's a very significant strength. And as a result, I end up using heat treated aluminum alloys for aircraft and spacecraft and things like that. The Space Shuttle main tank is made out of 2219 aluminum copper alloy. Okay. The problem is when I weld these things, I destroy the heat treatment. I end up with significantly less stress. A good rule of thumb is the weld will support 1/2 the strength of the base metal in a welded heat treated aluminum alloy. So if I get 60 KSI strength and I want to weld it, I'm going to get half the strength in the weld that I have in my base metal. And that leads to all kinds of design issues that we can talk about tomorrow. Okay? Yep. Who was working at General Electric in their 50s, I think, basically showed that if you put nickel and you go up to like 1,000 degrees centigrade, with a little nickel catalyst, you can take carbon, you can put it in a tetrahedral anvil press and make diamonds. But yeah, they're and it turns out artificial diamonds are expensive, but they're not, well, the problem with diamonds is all artificial cost anyway, because De Beers has got a worldwide monopoly, and they control the amount of diamond that goes into the market, and they control the quality of diamond, and they have warehouses full of industrial diamonds. But De Beers is actually making the industrial stuff now too, the synthetic stuff. But the synthetic stuff is actually better than the natural diamond for cutting tools because it has fewer defects and it's actually a little stronger. It's more uniform. Okay, enough on diamonds. That's right. It's a good point. In fact, I meant to mention that. Anybody know why diamond can't cut iron? Because iron and carbon alloy. And you get very high temperatures at the tip of the diamond. You get 1,000 degrees. The carbon just goes into the iron. So you have to use cubic boron nitride for working on steels. So, and in these tetrahedral anvil presses, we can make all the cubic boron nitride we want. And boron nitride, think about it. I mean, boron nitride is basically the same bonding as carbon. It's the same diamond lattice. It's just you alternate boron and nitrogen, and you still got, from one you get 5 electrons, to the other one you get 3 electrons. Carbon you get 4 and 4, right? Still 8 electrons, and you get the same type of bonding. But boron and nitrogen don't mix in steel, don't dissolve in steel. And so you actually have chemical dissolution of diamond when you use it to grind steel.
So diamond wheel and steel, they're actually whaling the diamond.
Yeah. Yeah, this wheel is as nasty as it seems. Be great on aluminum. Be great on most nickel alloys. Would not be so great on titanium. Would not be so great on steel. So this type of grinding wheel has very limited application, unless it happens to be cubic boron nitride. I don't know. I mean, the same company makes cubic boron nitride, and this very well may be cubic boron nitride. I haven't analyzed it. It's just a sample. No, I think it's similar cost, and I think it's about, is it less expensive than diamond? Oh, 25%. But for the grit, you're probably talking $10,000 a pound. Okay, for the product, which is not so. You're not using a lot of it on there. Plus, it's fairly light. It's lightweight material. So anyway, okay. Other questions? No. The carbide's already reacted fairly well, so it's not going to dissolve any more carbon. Other questions? Okay. We were talking about joining of aluminum, and the thing is, with aluminum. You're alloying with copper, magnesium, zinc, and silicon. There's 2 regions that you tend to develop your aluminum alloys. One is over here in the high aluminum alloys, and the other one is over here near the eutectic. You try to avoid this range in here where you have a wide freezing range. This is the liquidus, and this is the eutectic line, and this is the solidus over here. But this is basically where the material becomes solid. If I have a very wide mushy range where I have liquid and solid coexisting, that means that on freezing of that weld, I will have a wide temperature variation where it's mushy, and I'll have a lot of thermal contraction, a lot of thermal strain, and I'll basically get cracking. What we call hot cracking, or what a caster calls hot short cracking. Okay? We call it liquation cracking in welding, but casters call it hot shortness. Now, this, you don't have to be able to try to read this, but these are a bunch of different aluminum alloys going down here, and all I really wanted to show is this is iron. There's not a lot of iron in these things. There's not a tremendous amount of copper in most of these alloys. There is 3.3 to 4.7. There's a lot of copper in that alloy, but everything else is down less than 0.3% copper. If you look at magnesium, you find a bunch of alloys that are no more than 1% magnesium, and then you see, well, there's one here that goes between 1.1 and 1.8, but then you see everything jump up to 2 or 3 all the way up to about 5% magnesium. And what you've done is, by looking at either copper or magnesium, you're either very lightly alloyed or you're very heavily alloyed. And you avoid this region in between because of the tendency to hot crack because of wide freezing ranges. Wide freezing ranges are bad in welding in general, not just in aluminum alloys, because of this tendency to build up strain in the liquid solid mushy region. And if you were to look at some of the other alloying elements, you'd find similar types of things. But this is just kind of illustrating, if you look at aluminum alloys, you'll see the gap between the lightly alloyed and the highly alloyed aluminums. Turns out most of your aluminum casting alloys are the very heavily alloyed, way over here. Why? Because they're lower melting. It's easier to cast, and you can get some pretty good properties in them. Now, well, one of the problems I mentioned was quite often, whether you're talking the non-heat treated aluminum alloys, the 5000 series aluminum alloys, where you can get up to 40 KSI yield strength, but more typically you might get 30 KSI yield strength. Now, a garden variety steel will give you 30 KSI yield strength. It's difficult to find steels that give you less than 36. There are some, but in general, a high strength solid solution non-heat treated aluminum alloy, it's hard. You can get up to 40, but it's hard. In general, you get about 30. When you weld that, you can come pretty close to matching the base metal strength if it's 30. You'll have a hard time if it's 40. The Navy at one time had a program to try to develop a solid solution aluminum alloy for light, hydrofoil type of craft and things that was 50 KSI. And then the funding got pulled from them, but this was going to be a pretty high-tech processing and putting all kinds of metastable alloying elements and rapid solidification technology and stuff to make this alloy. You probably could, but you still were going to have some problems when you weld it of losing some of that strengthening that you did. The heat-treated aluminum alloys that can go all the way up to 70 KSI strength, you're going to have a hard time getting more than about 50% strength. What you're going to have is a soft base metal. And if you were to look in look at the hardness across the weld metal. So if this is my weld in the aluminum, and this is distance, I'm going to plot distance across here, and you were to look at just do an indentation hardness, you'll have high hardness in the weld metal because you're essentially going to make a highly alloyed casting, and then it will drop off fairly precipitously, and then it will come back up to the full base metal hardness. So I have this weak heat affected zone. I have this significant weakness in the heat affected zone. And I may have mentioned briefly here, but one time, 20 years ago, well, it wasn't 20 years, maybe 15 years ago, I was asked by Lincoln Lab to look at some aluminum welds that they had made for the Altar antenna out in Kwajalein. Kwajalein is an island in the middle Pacific, and about the only thing on Kwajalein is a Air Force, actually several different services, have these radar dishes, but the big radar dish at Kwajalein is about the size of a football field. And originally it was, I think it was built for some research purposes, but it turns out it's the right frequency that it could pick off any satellite going into or being launched into orbit by the Soviet Union. And so all of a sudden, the Kwajalein radar, which was designed like 45 years ago, is now at about 1,000% of its design lifetime. Okay, it's been used 10 times as much as anyone ever originally expected. And whenever it has to go down for repairs, it's classified, or used to be classified, because that would be when the Soviets could send a satellite up and we wouldn't know what its orbit's going to be. But Kwajalein radar, Altair could track it well enough on the launch that it could predict what the orbit was going to be before it got to orbit, which was important to know. Anyway, what had happened is they had these 4 long tubes, these are like 50 meters apiece, that basically hold up the main structure, and they had originally designed it so the welds were going to be between the plates of aluminum. This was like 6 or 10 feet in diameter, I can't remember, I never saw the real thing, but they had some longitudinal welds between the plates, and then they had a circumferential weld, and they beefed up these circumferential welds because this was a heat-treated aluminum alloy, and they knew the welds only had about half the strength they were supposed to have. So they designed the in welds with extra support, gussets and things, to transfer the load across the weak weld. And of course, these were longitudinal welds, so they were basically just in shear. They didn't need great strength. But then someone decided in fabrication that the size of the plates came such that they wanted to put another circumferential weld at the quarter points, not just the half point. Of course, the designers didn't know there was going to be a weld there, and so they didn't put any gussets there. And so when someone finally realized 25 years later that the fabricators had kind of added an extra weld that wasn't in the original design, and realized that aluminum alloys don't have the same strength welds, they said, oh gee, is this thing going to fall down? Of course, they went back out and they welded gussets in to protect those welds, but they cut out a couple of samples and they wanted me to evaluate how weak were these welds. Turns out we did this kind of hardness traverse, and we actually had some welds that were from the longitudinal welds, and we had some of the circumferential welds. If you looked at the hardness of the longitudinal weld, which had never yielded, never seen stresses in service, plus you have to recognize, you know, no one really quite knew when they designed this, and even 15 years ago, what the effect of a hurricane coming through here was in terms of what the real stresses really were on this. But on the other weld, the weld that had been the circumferential weld, so this is the longitudinal, and the circumferential weld had a profile like that. And from that, I was able to tell them, if I remember, 26 KSI, that hardness was equivalent to 26 KSI. This was like 18 KSI down here, and the strength of the material was supposed to be like 30 KSI. I was able to tell them that over the previous 25 years, the maximum stress that thing had ever seen was 26 KSI, because I had work hardened it to 26 KSI. The hardness had been raised because the material had yielded up to 26. So now we had, I mean, the material itself had the history of the maximum load it had ever sustained. So it's kind of a neat little way to figure it out. Then go back, the designers can go and figure out exactly what they got. Another story, since we ought to end on a story in this class, right? Start on stories and end on stories. I was called up once, big rush. I was busy. This was 12 or 13 years ago. Big rush by Raytheon out here in Waltham, where they were building the electronics for the Aegis missile system. Or actually, it was Aegis or the Phalanx? Yeah, Aegis cruiser. This is the Phalanx radar. They were building Phalanx. Okay, Phalanx. Yeah, Phalanx or something, right? How you Phalanx? Phalanx. So they were welding like 1 inch square solid 6061 T6 aluminum, and they were putting the electronics into these frames. So these were just frames to hold the electronics for the radars that were going to go on ships. And they called up and said, we've got a problem with aluminum welding. Can you come out? Well, I had something all day that day at MIT. And I said, well, why don't you call Professor so-and-so? He's the Alcoa assistant professor. He ought to be able to help you on an aluminum problem. So this young professor didn't have a car, so they sent a taxi to pick him up, and he goes out to Waltham, and he comes back at the end of the day, and his advice to them is they ought to have me come out and look at it. So I get a phone call, and they say, it's like 5:30 in the afternoon, and I was about to go home, and I said, okay, you're in Waltham, I live in Belmont, I will stop by on the way home. Will there be anybody there at 6 or 6:30 tonight? And they said, yeah, we'll wait for you. So I go to the plant, and what had happened is they had their people welding up these frames to put the radar sets in, and there was some distortion on one of them, and so one of the people was using an oxyacetylene torch to heat it up to bend it back. And the Navy inspector comes by and says, where's your procedure on that straightening where's your write-up procedure on that process? And the guy says, well, he's just an hour. He shrugged his shoulders. So the inspector goes to the engineer and says, where's the procedure? And they said, we don't have one. You're not supposed to heat up, for bending heat-treated aluminum alloys. I told you yesterday that they're tempered at like 250 degrees. You over-temper them and they're going to be weakened, right? Shut down the whole plant. 600 workers, whole plant shut down. Can't ship any product, nothing, That's why they were in a hurry. So I go by that evening, and they explain this to me, and I say, well, Now, this is another one of these things you don't know what's going on, you know. And I said, well, show me the operation. So I got to see this operation. It's a typical welding operation. I see the parts they're welding, and they've been doing everything they could that day, making up test ones and heating them at different amounts and trying to see if they bend and all this other stuff. So I look at all this and I go in and I say, well, let me see the drawing. I look at the drawing, and it turns out these are like inch or inch and a half square solid pieces of aluminum. And on the drawing, if you looked at it, so I'm going to weld one of these to another one, they were only calling for a partial penetration weld. You had 4 welds around this thing, but the center core wasn't welded at all. So this is the weld to another tube, continuing on. The center half wasn't welded at all. This might be a 1/4 inch penetration, 1/4 inch, and I had a 1/2 inch by a 1/2 inch inside this thing that wasn't welded. Well, clearly they weren't looking for full strength. Plus, if they only had half of, or actually had a little bit more than half the area welded, but the whole thing up here only had half the strength in the heat affected zone anyway. So what does that say about the design? It says the design here, this is a deflection limited structure. This is not a strength limited structure, this is deflection limited. You want it stiff so it doesn't bow and everything like that, but you don't need the strength. I mean, calculate the strength of a 1/4 inch aluminum weld 4 inches long. Okay, 4 inches. It's 1 square inch. 1 square inch at 20 KSI. The thing will support 10 tons. I'm just putting electronics in there. How much does it weigh, right? So it clearly was a deflection limited design. And so, in fact, what did I care if the person's heating up this thing, which had about, actually it was 60, 61, so it had about 40 KSI up here in the base material. And they had done some tests on heating these things with torches and found they were lowering the strength down to maybe 35 KSI. What did I care if the whole weld joint would only support 20 or less, right? The whole weld joint would only support about 10. So I wrote a letter. I had to go to Penn State the next day. So I went home, 11 o'clock that night, wrote the letter, dropped it off before I went to the airport. My secretary typed it up, and I think maybe they faxed it to me. I don't know. Anyway, they take it in. Raytheon takes it into the Navy, and they finally get the plant started up 2 days later. Okay, 2 days after. But you have to kind of go and say something like that. What was the designer's intent? What do you really need in this case? And yes, they had screwed up. It wasn't an approved procedure, but in this case, we could let it go because we had justification. Plus, you had a scapegoat. You know, I mean, people just want someone like me to take responsibility for it, right? It's not an uncommon thing. In fact, to finish with one last story, since I still got 2 minutes, there hasn't been something like that occur for more than about a week and a half. At least in my life. I get a call about 3 weeks ago from an engineering firm up here in Arlington, which is a spinoff of a bunch of old MIT professors of civil engineering. There's about 180-person engineering firm now in San Francisco and Boston. They designed Epcot Center, the big dome. They designed the big dome at the World's Fair in '64. They're very sophisticated structural engineers. Well, the problem is, for the big dig, they have these big clevises that hold up the roof panels, and there's about 20 of these clevises. They're like 1.5 inch diameter. If you want to see them, they're down in the lab. We're a couple of them. So these great big threaded rods with clevises on the end that basically connect from whatever the structure is on the top of the tunnel to hold the false roof. And these, I can't remember what these panels weigh, but you got 20 or so of these holding each panel. And they're originally, I can't remember how many tens of thousands of these are going to be in holding up the roof of the tunnel in the big dig. And it turns out the spec for the big dig said that this was supposed to be galvanized steel. Okay? And it says very clearly that before you drill any holes, or after, you should do your galvanizing, your hot dip galvanizing, sticking it in molten zinc, after you drill the holes, so that you don't have any bare steel areas. Well, the company in Cleveland, who makes millions of these for different construction projects around the world, Didn't do that. They drilled the holes after galvanizing. And so I have this galvanized clevis pin, which is about 1.5 inches in diameter, going through these holes. The rest of it's covered with zinc. And some of these have been installed for 1.5 years. And they were now telling the company that had sold these, someone had seen some rust down in one of these holes. And they were telling them, you're going to have to replace every one of these clevises. So we're going to have to, you know, the big dig is 1/3, you know, 1/3 of the roof is already hung, right? And they're going to have to replace all the others. And they said, we want hot dip. We don't want cold galvanizing where you spray some zinc powder in there. So what do? Well, first of all, you determine whether it's really a problem. Well, I looked at it, and you wouldn't know this, but it's not a problem, okay? I mean, this is basically a warehouse. If I had a galvanized pail, well, by the way, the lifetime of this is 70 years, okay? It's supposed to be the design lifetime is 70 years. If I had a galvanized pail sitting in this room, do you think the galvanized will be there 70 years from now? Sure it will. If I had it sitting outdoors with the rain hitting it, you think it'll be there 70 years from now? No, it'll be gone in about 30 or 40 years, okay, with just regular rain. And you know that if you've ever seen galvanized guardrails on the highway. 30, 40 years old, the rain hitting them, wet, dry conditions, they last 30 or 40 years. You can actually go to the metallurgical literature and you can find these numbers, okay? Now, if I actually sank it in salt water, how long would the zinc last? A year or 2, okay? So you have 3 different types of conditions. You have continuously wet, where the zinc's going to last, you know, the galvanizing is going to protect the steel for a year. You have it completely wet atmospheric exposure, where it'll last for 30 years, or you have it in a dry condition, where it'll last for, turns out there's data in the literature, I calculated it'll last for about 1,000 years, okay, before it oxidizes away, if it's continuously dry. So what did the designers intend? Well, the designers had to intend that the roof up above the thing was something better than just atmospheric exposure, which is sort of true. I likened it to, basically, it's an unheated warehouse, right? So how did I try to get, I mean, if the company had a problem, I would have told them they had a problem and you got to replace them all. But I knew this wasn't a problem. So how do you write a report when you have all kinds of people breathing down your neck, wanting to kill you, okay? And just because you got some metallurgists from the MBTA, who's saying, oh, you have to replace these. I mean, it's purely an emotional argument, right? It's going to cost millions of dollars. It's going to bankrupt this little company. It's also going to slow down the big dig for another period, right? Do we need to increase the cost of the big dig? Okay, so what's the right thing? I know what the right thing to do is. How do you prove it? Well, we had a week's time before this meeting that I couldn't go to. I sent someone else. But we put some of these things through a salt spray test. I stripped the zinc from one of them. I left the zinc on the other one that had the uncoated hole. I put the zinc-coated clevis inside each one of these holes and put them through a weak salt spray. Well, guess what happened? The one that still had the zinc on the outside but no zinc in the hole, with the zinc clevis going through the holes, no rust. Why? Because it's in contact with zinc. The clevis protects and the other zinc around it. Zinc has throwing power. Okay, it will protect things some distance away. That's why you can put a zinc on a propeller here and it'll protect, or you can put it on a propeller shaft over here and it'll protect the propeller several feet away. Surprise, surprise, okay? As in a continuously wet environment. Well, salt spray is a kind of wet, dry condition. And then we have the one that has no zinc on it, but I put the galvanized clevis in it because we still had galvanized pins, right? Not galvanized clevis, but I stripped all the zinc, and it was just, it looks terrible. Okay, we probably, I don't know, they probably still have it, but it looks terrible, rust all over, except in the hole, because it was protected by the zinc from the pin. So that kind of proves that it's not a problem. And then I calculated that we either have completely wet, dry atmospheric conditions, as if it's sitting outdoors and being rained on every day, in which case your design is only good for 30 years originally, whether you had zinc there or not, or it's completely dry, in which case I calculate the lifetime based on the literature of 1,000 years. So all I could tell them was that the lifetime of a properly made hanger was somewhere between 30 and 1,000 years. Okay? But the ones that didn't have zinc in the hole, I had the hole was 5% of the surface area of just the bottom part of the clevis. And therefore, I had 5% less zinc than I originally thought, which now meant my lifetime was 28 years to 950 years. Okay, so is any one of these engineers there going to stand up and swear that we calculated this out, that it's going to last for 70 years with this amount of zinc on there? First of all, this is all based on the minimum amount of zinc, according to the specification, and the people applying the zinc always go about 10 or 20% above that. So we're talking about a 5% difference when you've already got a 10 or 20% overage, right? So the Big Dig didn't get defective hangers like the MBTA metallurgist was saying. I mean, this guy, you know, he had a cause and he was going to stick it to this little company. Now, if the little company had made a mistake, I would have said, yeah, you made a mistake and you're going to have to fix it. But sometimes you need someone, it's not just coming in and saying, well, I'm a metallurgist and my qualifications are better than your qualifications. You have to figure out how to say it so people can understand it. I basically was writing my report to engineers, and I didn't make a commitment other than it's good for either 30 or 1,000 years, somewhere in between. If it's only good for 30 years, you had a fundamental design problem to begin with. If this thing is wet all the time, you got a problem. If it's not, then you don't have a problem. And in any case, if you think you calculated it within 5%, then maybe you ought to stick it to this little company, right? You start putting it in terms like that, and they didn't make a decision at the meeting a week ago, Tuesday. I wasn't there, but they were going to take it under advisement. But I guarantee you, all the construction managers there, after they had my ammunition, were not going to let that little MBTA metallurgist stick it down this company's throat, because they didn't want to delay the project anymore. They just wanted some scientific justification that it was okay to leave this stuff in place. Okay, but you know, it's not just enough to know it's okay. You got to figure out how to say it in a way that other people are going to be able to figure it out for themselves. Okay. Well, thanks.